Hello everyone. This is continuation of lecture 5. Last time we discussed normal distribution and several probability mass functions for discrete random variables. So today we are going to talk about some other distributions which are closely related to univariate normal distribution. One of them is chi-square distribution. So suppose you have n standard normal variables, zi, denote each of them as zi. I is index set, which goes from from 1 to n. So, and we are supposing that all of these standard normal variables, they are IID, independently and identically distributed, and obviously they have mean 0 and variance equal to 1. That is the definition of standard normal distribution. Okay, then the quantity, which is the summation of squared standard normal variables, that is going to be chi-squared. That quantity is going to have chi-squared distribution with n degrees of freedom. That is the important parameter of this distribution. If you remember, for normal distribution, we had two important parameters, which define the complete shape, define everything about the normal distribution, right? Mean and variance. In the case of chi-square distribution, the degrees of freedom parameter is the only parameter that we need to define the whole distribution. Okay, so usually we use chi-square distribution to model the variance or standard deviation, and the reason is we know that the variance cannot be negative because that is the sum of squared deviations, average of sum of squared deviations from the mean, and that cannot be negative. And if you pay attention to this quantity y, that is also always positive, as that is the sum of squared normals, right? So therefore, to model the non-negative quantity, which is, for example, variance or standard deviation, we are using chi-square distribution. And it has, as I mentioned, one important parameter, and that is the degrees of freedom parameter. And there is chi-square table. So the support of chi-square distribution is non-negative. You can see it will have a shape like this. It's going to be right skewed. So here you have x values, and here you have the probability density function values. If you draw the chi-squared curve, chi-squared density, it will have this kind of shape. So you can see that its support is always non-negative. Okay, so there is another distribution that is very much alike to chi-square distribution. Actually, that is the ratio of two chi-square distributed variables. Suppose you have two variables, y, which is chi-square with n degrees of freedom, and x, which is chi-square distributed with m degrees of freedom. And if you take the ratio of these two variables, then this quantity, this q, is going to be f distributed, and f distribution has two important parameters. One is n, that is called degrees of freedom in the numerator, and the second is m, that is called degrees of freedom in the denominator. Okay, so this is the f distribution, and usually we are using f distribution to make inferences about the equality of two population variances or two population standard deviations. And the third important distribution that is closely related to standard normal distribution is t distribution. We actually make use of it a lot. So suppose you have a quantity x, a variable x actually, that is actually equal to z is standard normal, and divide by some chi-squared variable, chi-squared distributed variable, which is y over n, right? We know that, define y in this way. Y is chi-squared distributed with n degrees of freedom. And then if you take the ratio of these two things, then the result is going to be t distributed, and t distribution has an important parameter that is also degrees of freedom. It has only 1 degree of freedom. Okay, so in this particular case, because the denominator is a chi-square variable normalized by its degrees of freedom parameter, then the resulting t distribution is going to have n degrees of freedom. Okay, so let's make a fast review of what we have talked about. So we have first chi-square distribution, that is basically the distribution of sum of squared normals, sum of squared standard normal variables. Okay, and it has one important parameter, and that is the degrees of freedom parameter n. Right. The second important distribution related to chi-squared, random variables is, or chi-square distribution, is f distribution. F distribution has two important parameters. Okay, unlike the chi-square has only one. F distribution has two of them. One is the degrees of freedom in the numerator, and the second is degrees of freedom in the denominator. And third distribution is t distribution, and t distribution is closely related to standard normal distribution. So you have z, which is standard normal, it has standard normal distribution, and y, which is chi-square distribution distributed with n degrees of freedom. If you take the ratio of these two guys, then you're going to receive t distribution with, the resulting variable is actually going to be t distributed with n degrees of freedom. Usually we refer to that as the student's t distribution, because the author who came up with this, he was using the nickname, pen name student. Therefore, sometimes this is referred to as student's t distribution. For all this distribution, for all these three distributions, we have, tables. We have chi-square table, f table, and t table, and obviously we have z table. We have talked about that. So these tables, they are basically giving you the area under the corresponding curve. For example, if you look at the chi-square table, you are going to find the areas, the areas to the right of this particular value, chi-square, value, let's say some outcome of this, actually some outcome of chi-square distributed random variable x bar, like chi-square bar, let's say. Okay, and that table, chi-square table, is going to give you the areas, the integrals, so you don't have to compute the integrals all the time. Okay, now let's look at the asymptotic behavior. Asymptotic behavior means when n is large. Okay, and one more word of caution, this chi-square ft, they don't have convenient analytical forms for their cumulative distribution functions, but that is not a problem. We have tables, right? So if CDFs are not well defined, if they're not easy to work with, then you're gonna have tables. I mean, for pivotable distribution, we basically have tables which give us the value of the CDF function, or you can say the area under the corresponding curve. So now let's have a look at the asymptotic behavior of these distributions. Let's see what happens when n is large. So when n is large, chi-square distributed random variable, if you divide that by n, by number of standard normals that we are summing, the square of which we are summing, actually, because we said that if y is sum of squared normals, so this is standard normal, I goes from 1 to n, we know that this is actually going to be chi-square distributed with n degrees of freedom, right? So if this n goes to infinity, and if you divide this guy by n, as n goes to infinity, then the result is going to approach to 1. And regarding the t distribution, as degrees of freedom parameter increases, as n goes to infinity, actually degrees of freedom is going to increase, and then t distribution is going to get increasingly alike to standard normal distribution. And therefore, in statistics, we say that if you have large enough sample, like something about 50 observations, you actually have the right to use z table instead of t table to get the associated probabilities, right? So that is the reason, because we know that as n grows, then t distribution approaches to standard normal distribution, actually it becomes increasingly alike to normal distribution. Now let's look at the third property. So chi-square random variable is actually going to approach to normality, normal distribution with mean n and with variance 2 times n. And that is the reason why we have, when we divide by n, the result is approaching to 1, right? And finally, the F distribution, if you have the, this is, the first guy is the degrees of freedom in the numerator, and the second is the degrees of freedom in the denominator. If you basically, if you have fixed, you see, let me write it here. We said that Q is going to be, if you have like 2 chi-square random variables, y, and if you normalize it by their respective degrees of freedoms, let's say y is distributed chi-square with m degrees of freedom. So if you divide it by m, and if you have another chi-square random variable x, and if you divide that by its respective degrees of freedom n, and once n goes to infinity, we know that the denominator here is going to approach to 1, right? By the first property, as n goes to infinity, limit n goes to infinity, we know that this guy is going to approach to 1, and the overall result is going to approach to y over m, which is a chi-square distributed random variable normalized by its degrees of freedom. So the result is going to be chi-square. Okay, so that is kind of simple, isn't it? Great. Now, regarding the p-varied normal, I don't want to spend too much time on this. This is about the derivation of the p-varied normal probability density function, but you don't really have to derive it for the purposes of this course. You don't really need that. So then we have conditional distribution of normal. You see, it is given if x1 and x2 they are jointly normal, then conditional distribution of x1 given x2 is going to have this form. Okay, and remember that in the previous classes we said that you might have 2 variables x and y, or x1 and x2, if they are uncorrelated. So if, let me write it in this way, if correlation of x1 and x2 is 0, we know that this is not implying that x1 and x2 are independent, right, of x2. We know this, but this normal distribution is kind of a specific case. In that case, actually, if x1 and x2 are normal, then that will automatically imply that x1 and x2 are independent. That is a specific case, you see. That's kind of exception to the overall, to the general rule. Okay, that is theorem 5.3. You have to know that. Then we have example 10. We have x and y. They have a p-varied normal distribution with parameters mu1, mu2 equal to 0, and so basically you have x and y which both are standard normal distributed, and the correlation coefficient rho, they are actually standard normal, but they have some correlation rho, so they are not independent. We have to find the distribution of the random variable z, which is actually ax plus b times y. In that case, what we can do is we can use the property of, we have to use this guy. We know that, if you have linear transformation of normal variables, the result is still going to be normal, right? We know that, and we can use the property of expectation and variance. We already know that z is going to be normal, but we don't know what is its mean, what its mean is going to be and what its variance is going to be. But we can find that. We can say that expectation of z is going to be equal to the expectation of, let's plug the definition of z. It's alpha times x plus b times y. So that is going to be equal to, I know that if alpha is constant, we can take it out of the expectation, and also expectation is kind of, a linear operator, meaning that you can apply it to each of these additive terms separately. So this is going to be alpha times expectation of x plus beta times b times expectation of y. And we know that by the rule, we know that x and y, they have mean equal to 0. So this guy is going to be 0 and this guy is going to be 0, and as a result we're going to receive 0. Okay, so we have already found the mean. So the resulting variable z is going to have mean equal to 0. And now let's find the variance. Variance is also easy to find. Variance of z is actually equal to variance of alpha times x plus beta times y. And we know that you can rewrite it as, you can say that, oh, maybe I have to start a new page. Just a minute. So let me write it. This is example what? This is example 10. So example 10, we can rewrite it. We can say that, z is equal to alpha x plus b times y, and we know that by theorem we know that z is normal, but we don't know this and this. Okay, we said that the expectation of z is going to be equal to alpha times expectation of x plus beta times expectation of y, and as a result, because this guy is 0 and this guy is 0, as a result we receive 0. So let's plug 0 here. Regarding the variance of z, we can say that this is equal to variance of alpha times x plus beta times y, and then you can rewrite it as, we know that the variance of a plus b is actually equal to variance of a times x plus variance of b times y plus, plus 2 times covariance of x and y. But here you have alpha x and beta y. Actually, you don't have to, you have to remember that. So you have two variables, alpha x and beta y. So here we talk about covariance of alpha x and beta y. So we know that we can take this beta out, like alpha and beta out. We have to square them. So this is alpha times, let's call the variance of x as sigma square. And we know that by definition we have sigma square x and sigma square y equal to each other. So you can rewrite it as beta square times sigma square. And then you have plus 2 times covariance. In the case of covariance, what we can do is we can rewrite it as 2 times a times b times the covariance of x and y. This is the property of covariances. And then what else we can do? We actually know that, you have to use the correlation coefficient, basically. So you have to express covariance by correlation coefficient. We know that this is going to be equal to, covariance is actually equal to, let me use red line. So covariance is actually going to be rho times sigma of x times sigma of y, but as long as these two guys are equal to each other, so you're going to have sigma square here, right? So rho times sigma square, and as a result you receive what? You receive sigma square times a square plus b square, and plus 2 times a times b times rho, right? And that is basically the variance of the new variable. Let me rewrite it here. We can say that z is going to be normal by theorem, because theorem is telling us that linear combination of normal variables is still normal. So it's going to be normal with mean 0, but with the variance of sigma square times alpha square plus beta square plus 2 times A, B times rho. And that is all. That is the solution. Okay, now let's have a look at question 11. In question 11, we have population married couples. Height of X hash belongs to height of husband. XW belongs to the height of wife. And we have p-weight normal distribution. And mean heights, we have mean heights. And the variances are equal. And rho is given. So if the height of the husband is 6.3 feet, what is the probability that his wife has a height between 5.28 and 5.92? So we have to get the conditional distribution, right? So you are fixing the husband's height, right? It means that you have to get the distribution of wife's height given the husband's height. Okay, we have to derive that using this animal here. Okay, and then after that we have to derive the probability. Okay, let's start a new page for that. Example 11. Okay, and so what we have is, we know that if this is the height of women, then the conditional probability of women's height given the husband's height is fixed. So it's fixed at some value x hash. It's gonna be normal. So we assumed normality. It's gonna be equal to, so the mean is gonna be equal to mu of wife plus the ratio of standard deviations, sigma of wife, sigma of husband, times rho, correlation coefficient, times x2 minus mu2. And the variance is going to be equal to, so the variance is going to be equal to sigma of wife times 1 minus sigma square of wife and 1 times rho square. That is the variance. So in this particular example, what we do is we say that, so suppose husband's wife is fixed at 6.3 feet. So here actually we say that x of wife given x of husband is actually equal to 6.3 feet. In that case, we know that it's going to be normal, and the mean height of wives is equal to 5.3. Okay, 5.3. Then the variances are equal to 0.2, so the variances, they cancel each other out, plus, and we have x2. We fixed x2 to be equal to 6.3 minus the mean of husbands is actually equal to 5.8. Okay, that is going to be our mean. And regarding the variance, it's going to be equal to sigma square of wives, which is equal to 0.2 square times 1 minus rho square. So 1 minus 0.6 squared. Okay, great. Now if you want to get the probability that the wife's height is in between 5.28, this is capital X, and 5.92, given husband's height is fixed at 6.3. For that, you have to actually use the conditional probability density function. Okay, and we have it. we know that the conditional mean is going to be equal to this guy, which is, let me calculate that, just a second. So let me rewrite it. I calculated these things. So this guy was equal to 5.8, and this guy turned out to be 0.0256, right? So if you want to find this probability, you have to normalize. You have to say that I'm going to convert it to z. So it's going to be 5.28 minus the conditional mean, which is 5.8, divided by the standard deviation, which is square root of 0.0256. Let me find that. Square root of 0.0256. That gives you 0.16. And then that is going to be less than or equal to, automatically the x variable is going to be converted to z when you do this transformation. Now let's do the transformation on the right side. So 5.92 minus the conditional mean, which is 5.8, divided by 0.16 again. So for that you have to use the z table. So this is going to be equal to, so this is going to be equal to minus 3.25 z, and here we're going to get 5.92. In that case you receive 0.75. I hope the arithmetic is correct. So this is how you do that, and the rest is easy, right? So you have distribution, z distribution, or standard normal distribution actually now. So the standard normal variable is z. Okay, z has many values here. It's actually symmetric around 0, we know that. And then what you have to do is you have to get the value between minus 3.25 and positive 0.75. Okay, so you're interested in this area, and we know that this area can be found by finding z, which is probability of z being less than or equal to 0.75 minus probability of z being less than or equal to minus 3.25, and we know that this guy is actually, it's approximately 0, so you can actually drop that. This is going to be equal to probability of z being less than or equal to 0.75. So just check the z table and find the corresponding probability. Okay, that is the question. That is the 11th question, and let's have a look at 12th question. What does it tell us? So we have normal variable, two normal variables, and the only difference between them is they have different means. For the first one we have mu, and for the second one we have mean equal to gamma. And then we are supposing that they are independent, and you have two other variables which are linear combinations of x and y. So u is the addition and v is subtraction. What we have to do that, we have to say that u and v are independent normal variables. Okay, for that what we have to do is first we have to get the distribution of u, then to get the distribution of v, and then if you can pin down the fact that u and v have zero covariance or zero correlation coefficient, that is sufficient to prove that these guys are independent, because we have mentioned in this theorem that only in case of normal distribution, if you have two normally distributed variables and if they have zero covariance or zero correlation coefficient, then that automatically implies that those two guys are two random variables, they are actually independent. For other distributions that doesn't really hold. That is, the reverse of this implication is not correct. Usually we say that when you have independence, you have zero covariance. We know that, but not vice versa. But only in normal case that exception actually holds. I mean, this implication is two-sided, bidirectional. So zero covariance implies independence, and independence implies zero covariance, only in normal case. So that is still easy, right? We can do that. Let's go to a new page, example 12. Okay. Example 12, it tells you that you have u, so maybe we should start from x. X is normal with mu and sigma square, and y is also normal with gamma and sigma square. So the variances are equal, but the means are different. So we have u, which is equal to x plus y. So we know that that is going to be normal, but we don't know what is its mean and what is its variance, right? We don't know them. Let's find that. So we know that the expectation of u is going to be equal to expectation of x plus expectation of y. We can rewrite it in that way because expectation is a linear operator, meaning that you can apply it to each term of addition separately. And expectation of x is mu, expectation of y is gamma. So it turns out that this guy here is going to be mu plus gamma, right? The expectation of u is going to be mu plus gamma. Now let's have a look at the variance. So what is variance? We don't know. Let's see that. So this is, maybe I have to use some, okay, let me use this rectangle and use a thicker line. Maybe use red, or maybe use some other color, pink. Okay, now let's move to the variance of u. We know that the variance u is equivalent to variance of x plus y, and that is going to be equal to, due to independence, that is going to be equal to variance of x plus variance of y. So there is no covariance term because we have assumed independence. So that is going to give you 2 times sigma square, right? We know that variance of x and variance of y, they are equal to each other, and they are equal to individual, they're equal to sigma square. Therefore, we got 2 times sigma square here. Now let's have a look to the second variable. Maybe I have to use a rectangle here. Okay, and then let's use another color here, green one. Okay, now let's move to the variable v, which is equal to x minus y, right? I know that that is going to be normal due to the theorem telling that linear combination of normal variables is still normal. But I have to find the expectation and variance. But that is going to be easy in this case because, okay, let me rewrite it. We know that the expectation of the expectation of v actually can be written as the difference in expectation of x and expectation of y, because expectation is a linear operator, and that is going to give us the mu minus gamma, right? Gamma. And what about the variance? We know that the variance of x minus y is just sum of variances minus 2 times covariance, but covariance is 0 due to independence assumption. So it's still going to have 2 times sigma squared as our variance. Now what we have to prove is, we have to prove that, let me use yet another rectangle here, but probably using a different color. Oops. Let me use a different color here. Okay, blue one, why not? Okay, so if we can prove that the covariance of u and v is equal to 0, then that will imply independence because both variables are normal. This can hold only in the case of deviated normal case, right? So now let's do that. What does covariance mean? Covariance of u and v is actually equal to covariance between x plus y and x minus y, right? So we can rewrite it as, we know that covariance can be like that is also linear, so we can say this is equal to covariance of x with itself. So we are basically taking these two terms first, then x times y with negative sign, covariance of x and y, and then let me use another color. You're going to take yx and yy, right? But we have to keep the signs there. So it's going to be equal to plus covariance of xy and minus the covariance of y and y. And we know that by definition, by definition of variances, we know that covariance of variable with itself is actually equal to its variance. Okay, it's equal to variance of x, and that's equal to variance of y. But what else we assume here? Remember, we suppose that, we actually found out that the variance of u and v, they are equal to 2 sigma square. So we can plug it 2 sigma square minus 2 times sigma square, and that gives you 0. In the end, you got 0 covariance for u and v. So that implies that u and v are independent. Remember again, this is only for the case when both variables are normally distributed. Okay, great. Now let's move on. Which example we have? We have example 13. What do we have here? We have, okay, just let me, okay, we have example 13. We have variance covariance matrix. Remember, in the variance covariance matrix, the main diagonal elements, they correspond to variances, and off diagonal elements, they are referring to covariances. We have to find this ugly animal here. So the probability of this ugly animal, and remember, first to find the probability, we have to know the probability distribution, probability density function. So why not to derive the probability density function for this animal, x1 minus x2 minus x3. Now let's do that. Okay, example 13. Okay. Great. So we're searching for probability x1 minus x2 minus x3 is actually greater than or equal to 2. So for that we need to, let's define this variable as y. So let's find the y. What is the distribution of y? Y, we know that given that you have normal distribution for all of these three guys, we know that according to an important theorem, the linear combination of normal variables is still normal. So we know that this is normal, but we don't know what is its mean and what is its variance, right? Y is defined to be x1 minus x2 minus x3. Okay, for that we can use the expectation of x1 minus x2. Maybe I should start with y. So expectation of y is actually equal to expectation of x1 minus x2 minus x3, but we can rewrite it as, we can apply expectation to each additive term separately, and that is going to give us, so we suppose that all of them have mean 0, so you're going to receive 0 here. So expectation of x1 is 0, x2 is 0, and x3 is 0. That is what we have assumed. We have supposed that you have mean vector equal to 0. All means are equal to 0, then obviously this is going to be 0. Now the variance is going to be a little bit nasty here. So let's find the variance of this guy. Variance of y is going to be equal to variance of x1 minus x2 minus x3 which is actually equal to variance of x1 plus variance of x2 plus variance of x3, we know that. And here we have covariances minus 2 times covariance of x1, x2 minus 2 times covariance of x1 with x3 and minus 2 times covariance of x2 with x3, right? So if you look at the variance covariance matrix, so the first element here, let me show you. So the first element is actually, so the first element here is actually corresponding to the variance. So here you have 1, 2, 3, the row numbers, and here you have 1, 2, 3, the column numbers. So the entry corresponding to 1, 1 is actually giving you the covariance of the first variable with respect to itself. So covariance of x1 with itself is actually its variance. So 1 is the variance of x1, and 2 is going to correspond to covariance of second variable with itself. So 2 is the variance of x2, and another 2 is the variance of x3. That is obvious. Okay, and what else here? If you look at this, we have many zero entries here, but we got something. Let me use blue color for this. Here we got blue color. Within blue circle we have 1, which corresponds to 3, 2. That is actually covariance. That means that covariance of x3 with x2, which is the same thing as the covariance of x2 with x3, and that is going to be equal to 1. So, and also we have another one here, and that is corresponding to covariance of x2 with x3. You see, therefore off diagonal elements of the variance covariance matrix, they should be equal to each other due to this property, because covariance of x3 with x2 is the same thing as covariance of x2 with x3. So both of them is going to be equal to 1, and the rest of the covariances are actually equal to 0. Therefore, it's very easy, simple to solve. Okay, it's going to be simple to solve. Just a second. Okay, so here we said that x2 x3 covariance is actually equal to 1, and this guy is 0, this guy is also 0, and while the variance of x1 is 1 based on variance covariance matrix, variance of x2 is 2, and variance of x3 is also 2. And then we can say that the variance of the whole thing is actually equal to 1 plus 2 minus 2 times 1 is 2. So that gives you 3, isn't it? So it means that we have found y's covariance, and covariance of y is actually y's variance, and its variance is equal to 3. Now let's draw. Okay, put these full calculations within a rectangle. Maybe to use a yellow one for fun. Okay, great. Now we're ready to find that probability. That is actually probability that y is greater than or equal to 2, which is because y is normally distributed, we can use this normalization, standardization operation. So you take y, subtract mean, and divide by standard deviation, which corresponds to converting it to standard normal variable. So we apply the transformation, z transformation, to the left side. Let's apply the same to the right side too. So 2 minus the mean is 0, divided by square root of 3. And that is going to be equal to probability that z is greater than or equal to 2 over square root of 3, which is the same thing as 1 minus probability that z is less than or equal to 2 over square root of 3. Now, I will not computed, because this is basically, you have to look at the z table. It's basically corresponding to some area here. So we know that it's symmetric around 0. The standard normal distribution is symmetric around 0, and 2 over square root of 3 is actually corresponding to somewhere here. So basically you have to find the area to the left of this. Okay, and then subtract that area, subtract the red area from 1, and as a result you are going to get this green area. This green area is actually the one that you are searching for. And that is all. That is all about lecture 5. Okay, so I'll stop at this point. Next lecture is going to be about sampling. See you soon.